Hey everyone, in the next couple videos we will be looking at section 4.4. This section is rather long and requires you to be comfortable with the material from section 4.3. So I recommend you go back and revisit 4.3 before part 2 of this section. When I went back to revise the video on section 4.3, I realized that I did not give as nice of an introduction to 4.3 and 4.4 as I would have liked. So let's pretend this next bit happened one video ago. In section 4.1, we discussed the idea of optimization of a function using derivatives to help us identify points of interest, namely critical points. I'll remind you that derivatives are fundamentally limits, which only depend on the local behavior or the nearby behavior of a function. Yet, we were able to use them to get information about the global behavior of the function, specifically the absolute maximum and minimum. Section 4.3 and 4.4 are here to expand on these ideas by continuing to see how the local behavior interacts with the global behavior. Section 4.3 talked about using the first derivative to establish information about the local behavior of a function. This topic is extremely important, as reality is not often kind to us and only allows us to gather information locally. For example, in astrophysics, where we only have information about the known universe. Section 4.4, like the videos, is broken into two parts. The first part is similar to section 4.3 in that it'll study how to use the second derivative to understand information about the local behavior of a function. The second part is about using section 4.3 and the first half of 4.4 to approximate the graph of a function. This section is not truly about graphing a function, which in the modern day is usually left to computers anyway. Instead, this section is about a much deeper idea. How to take local information, in this case the derivative and second derivative, to gain some understanding of the global picture, in this case the graph of the function. So in part 1, we are going to focus on the concepts and terminology that we will need to understand the second derivative of a function and its connection to the function itself. This will resemble the second video that we saw in section 4.1. So once again, I recommend that you take the time that you need to familiarize yourself with the new words and concepts before moving on to part 2. So let's get on with it. So up to now, our class has focused on the first derivative of a function. This video will focus on the second derivative of a function, that is, the derivative of the derivative, often written as f double prime. In previous sections, we have studied the information contained in the first derivative of a function. For example, we have seen the first derivative gives you the slope of the tangent line at any given x value, or can be used to find where a function is increasing or decreasing, as well as the other properties seen here. Since f double prime is the derivative of f prime, it follows that all those same properties hold when you substitute f prime for f and f double prime for f prime. This is all well and good, but I'll remind you that our original goal was to study the relationship between f and f double prime. Before we do that, I will introduce a new concept that will play a central role in answering the question you see here. This new concept is the idea of concavity. The definition given by our book is seen on this slide, but it may not be entirely obvious what it has to do with the graph seen below. I want to point out that both these definitions have to do with when the derivative of f is increasing or decreasing. So our study of 4.3 should hint at the fact that this has a connection to the second derivative of f. Also, as you can see below the two graphs, the terms concave up and concave down can be replaced by the terms convex and concave respectively. As you see, the graph that is concave up seems to open upwards. Similarly, the graph that is concave down seems to open downwards. For the record, I made air quotes when I said opens, because this is by no means precise. So let's look at other ways to understand graphs that are concave up. I will mention that there is an equivalent version of all these for concave down graphs, but we will focus on concave up graphs to save time. One way to define a graph that is concave up can be seen here. We may say a graph is concave up on an interval if it has the property that at every point in that interval, the tangent line lies below the graph on that interval, except for at the point. You can see that besides those 2 points, those lines lie strictly below the rest of the graph. This definition is equivalent to the one our book gives, and is used by other calculus books as their definition of graphs that are concave up. Comparing the two, our definition makes it easier to see the connection between the second derivative and concavity, while this definition makes it easier to visualize graphs that are concave up. Another way to state the definition of concave up graphs can be seen here. We can say a graph is concave up on an interval if every secant line is strictly above the graph. As seen in this picture, both secant lines touch the graphs only at the endpoints and otherwise have higher y values. This definition has the advantage that you do not need derivatives or tangent lines to exist everywhere, so it can be applied to more functions. Also, this version of the definition has a clearer connection to the definition of convex polygons that you may have seen in geometry. This definition will not serve our purpose in this class, as it makes it harder to see the connection between the second derivative of a function and the concavity of its graph. Pardon the pun, but I'm going to go off on a tangent here. Some of you, such as industrial and electrical engineers, will at some point learn about either linear programming or more generally convex optimization. The word convex in this setting is very much related to what we are discussing here. In those settings, you'll find that this definition for convexity is far superior to the other two we have in this class. Now that we have the notion of concavity, we can refine our previous question to, how is f double prime related to the concavity of the graph of f? The red line seen here is the tangent line to the graph of y equals x cubed minus 4x at the point P. In a moment, the point P will begin to move towards the local maximum. Take a moment and pause the video if you need to, and ask yourself, first, what's going to happen to the slope of the tangent line as P moves towards the local maximum? Based on your answer, what does that mean about f double prime at the point P? Notice that right under the absolute maximum, there is a display of f prime at P. Feel free to watch it as P moves to get an idea of what's happening. So there's a big button that says push me. Generally, I don't advise listening to inanimate objects, but let's go ahead and click it anyway. As we watch it again, notice that the derivative at the point is decreasing to 0. This makes sense since it's going to a critical point where the derivative has to be 0, since f is a polynomial, and hence its derivative exists everywhere. So the derivative must be decreasing, but based on our definition, that means the graph is concave down. But also, that must mean f double prime is negative. Okay, so we're going to see another animation. This time I'm going to move the point P from the critical point down to the origin. Again, I want you to take a second and ask yourself, what's going to happen to the slope of the tangent line as you head towards the origin? Also, what does that mean about the second derivative? Okay, here we go. Let's push the button. Okay, well, it got steeper, but in this case, it got steeper in the negative direction, so it is still decreasing. That means that f double prime is negative. This should come as no surprise because the function continues to be concave down on this interval. For the next two clips, I'm going to go a little faster. Okay, the first clip is going to take us from the origin to the local minimum. The second clip is going to take us from the local minimum up towards infinity. So take a second and ask yourself, what's happening to the slope of the tangent line on each of the next two intervals? Also, what does that mean about the second derivative? Unlike before, now the slope is increasing, which means the second derivative must be positive. This makes sense because the slope starts at -4 and ends at 0. This time, we see that the slope of the tangent line is increasing, which is the same as saying the second derivative is positive. So let's look at the fourth clip really quickly. You might guess that because the function continues to be concave up, the second derivative will be positive. So let's summarize everything we've learned and try to draw some conclusions from it. First of all, on the first two intervals, the second derivative was negative. That seemed to be due to the fact that the function was concave down. On the next two intervals, the second derivative was positive. This seems to be caused by the fact that the function is concave up. So here's the animation one last time, but this time it also displays the second derivative's value at each point. So watch the second derivative and see that it is first negative, then positive, as the function is concave down and concave up respectively. Finally, I want to draw your attention to what is happening at x equals 0. Before x equals 0, the second derivative is negative. After x equals 0, the second derivative is positive. This means at x equals 0, the second derivative must also be 0. We call points like this inflection points. This theorem here summarizes exactly what we just observed. The graph of a function will be concave up when the second derivative is positive, while the graph of a function will be concave down when the second derivative is negative. So here are two examples of that theorem in action. First of all, the function f of x equals e to the x is concave up because its second derivative, e to the x, is always positive. The second example is g of x equals the natural log of x. In this case, its second derivative, negative 1 over x squared, is always negative on its domain. As a result, it is concave down. I chose these examples to point out that a function doesn't need to look like a parabola in order to be concave up or down. The last concept I want to introduce in this video is the idea of point of inflection. As you see above, it is defined as a point where the concavity changes from up to down or down to up. In the two examples depicted here, both functions are concave down on the green part and concave up on the blue part. In both cases, the origin, or 0, 0, is a point of inflection. So finally we ask ourselves, how do we find points of inflection? It turns out we already know how. We know that points of inflection must divide up an interval in such a way that the derivative is increasing before and decreasing after, or vice versa. That means points of inflection must be critical points of f prime. Since we know how to find critical points, we know how to find inflection points. The theorem at the bottom of the page is simply the theorem we had before for finding critical points, but it is instead stated for critical points of f prime, which are the inflection points. Finally, we're going to look at one quick example of how to find the inflection points and the intervals of concavity for a function. Please pause the video and give yourself an opportunity to try this problem before going on. So remember, we are looking for critical points of f prime. So first let's find f prime. To find critical points of f prime, we actually need its derivative, f double prime. We know the first kind of critical point occurs when the derivative is equal to 0. So the first candidates for inflection points will be when the second derivative is equal to 0. That doesn't mean that these are necessarily inflection points. We still need to check that the concavity actually changes. So we set the second derivative equal to 0, factor and solve. That gives us 2/3 and negative 1 as candidates to be inflection point. Normally at this point we would check for the second kind of critical point when the second derivative doesn't exist. But since in this case f double prime is a polynomial, we can skip this step entirely. To find on which intervals f is concave up and down, we create the usual chart to try to figure out the sign of f double prime. From this chart, we see that from negative infinity to negative 1 and 2/3 to infinity, f must be concave up because f double prime is positive. Similarly, from negative 1 to 2/3, f must be concave down because f double prime is negative. One of the other consequences of our work is that we've confirmed that both negative 1 and 2/3 must be inflection points as the concavity changes on either side of them. Okay, here's the graph of f of x from the previous example. I've marked the inflection points. You can see that the concavity changes at both these points from concave up to down to up. Wow, okay, this video went much longer than I thought it would. But as I said at the beginning, there is a lot of content to cover. Thanks for sticking with me through all this, and I'll see you in part 2.